body and some of the 5 common tests that are actually performed. But before we get into that, kind of a couple things I wanted to go over with first is assisting me today is Jim Kennedy. He is our host. If you have any problems or difficulties with the audio or visual presentation, please address those to Jim over our chat line, and he will do his best to go through and get those corrected as soon as possible to get you back up and running. If you have any questions concerning the material that is being presented, you can address those using our Q&A facility to Saeed, and he will either answer those questions directly over the Q&A facility, or he may interrupt and, if it's something that we're talking about currently at that moment, we may try to go ahead and interject and answer those questions at that time. So, but we will try to get to all of your questions, through this, presentation and stuff here. Like I say, we've only got an hour, so it's going to be pretty much just a quick overview of what these tests are actually designed to do, and a little bit on how they're actually being performed. So I do invite you to ask questions as we do go through the material. Okay, again, I started to go through the outline briefly, talking about type testing versus routine production line tests. Some of the things that we're going to talk about is what kind of effect does electrical current actually have on the human body? And we'll talk a little bit about what your perception levels are, your let go, your startled reaction, what type of current level does it take to actually achieve some responses of the human body if you do receive an electrical shock. Then we're also going to talk about the dielectric withstand test, how that is actually conducted, what it's conducted on, what's the purpose of it. We'll talk a little bit about continuity test of the grounding conductor within a product. Why is it important to have a ground system in the electrical product itself? What's the purpose of it? A ground bond versus a ground continuity test. We'll talk a little bit about touch current test, measuring the leakage current of the product while the product is actually operating. What kind of responses the human body could possibly have to potential shock hazards as a result of that type of current. And we'll talk also a little bit about insulation resistance testing, and how does that differ from a dielectric voltage withstand test or a Hipot test. Okay, so let's get started. What's a type test? Whenever we're talking about electrical safety test on products in accordance to agency standards, they're kind of split off into 2 different categories. One is the type test, or kind of an engineering test, that is conducted on a representative sample of your products based upon agency standards, where you will either your engineers or the safety agency that may be listing your product will actually conduct a bunch of tests on your product to make sure that it does comply to the safety standards that are designed for that type of product. And what do I mean by the type of product? Well, your product could be classified as maybe laboratory equipment or medical equipment or toys or appliances. And your standards typically are split up based upon these different categories because they all have kind of something in common, and the tests are classified for each of those type of categories. So when we submit a product to a safety agency, they will go through and conduct a bunch of different tests on the product, and they'll try to evaluate it for particular safety hazards. What kind of hazard could exist if the product is submitted to maybe an impact as a result of shipping. If the product is submitted to some type of a surge voltage test on the input, what effect could that have on the product itself? If there's an overload, if your product is designed to have a fan and the fan fails, does it create an overheat condition? So these are all different types of tests that are conducted as a type test to evaluate the design itself. When we talk about insulation of the circuits, the insulation category that is chosen when the design is actually being built should be based upon agency standards. How is that product actually used? What type of environment is it used in? Is it meant for outdoor applications versus indoor applications? The pollution degree. What kind of environment is the product submitted to? If it's got a fan in it, will that fan ingest a bunch of pollutants into the product that could decrease creepage and clearance distances that could create a shock hazard? So they kind of test it for both normal and abnormal operations to fully evaluate the design of the product itself. And this is all some of the things that a type test is actually designed to do. Okay, the routine production line test, on the other hand, is something that we would do on all 100% of the products that we manufacture. And these tests are typically done when the product is fully assembled. It's done at the end of the production line. Some of the routine safety tests that are done on the product itself, typically if the product is designed to have a grounded enclosure, a Class 1 product, where it is relying on a grounded chassis or grounded metal enclosure to provide the second line of defense to guard against an electrical shock. The first line of defense, of course, is the insulation within the product itself. The second line of defense is this grounded enclosure. One of the tests that is typically done is a test to ensure that there is continuity between the ground blade of the attachment plug to any exposed dead metal or the chassis of the product itself. And this test is required typically as a 100% routine production line test if you are testing a Class 1 product. Another test that is routinely done or specified is the Hipot test. And we're going to talk about that also today as we go through this. Why do they do these tests? These tests are done because they are essentially looking for defects in workmanship that could create a potential shock hazard. Could be possibly some reverse wiring, could be damaged insulation where maybe somebody has pinched wires, component spacing where you don't have sufficient clearance because the way a component was assembled within the product itself. Is there adequate, insulation? Has the insulation in fact been damaged during the assembly process? Was a wire pinched between two panels when the last panel was put on? So these are types of defects that can be caught during a routine production line test. And lastly, they'll go through and they'll make sure that the product functions. They'll turn it on and typically check to make sure that the product does do what it's supposed to do, that it doesn't blow the fuse when you turn the thing on, that it is going to, in fact, function as specified, essentially. So these are types of tests that are done as a routine production line test, typically at the end of your production line. Hazards that are normally evaluated as part of the product safety evaluation. The first one is electrical shock. The second is electrical or energy hazards, stored energy. That could be electrical energy, it could be mechanical energy, something that may be spring-loaded. If you pop open a panel or something, is something going to fly out and cause a particular injury, this type of thing. Fire hazards, mechanical and heat hazards, radiation hazards, chemical hazards. All of it depends highly upon the category or the type of product that you're testing and what is its actual function. So depending upon what the function of the product is, you may have different types of hazards that are evaluated on the product itself. Electrical shock. Whenever a person receives an electrical shock, it is usually because they themselves have contacted one point of a circuit that is energized and they themselves are grounded, because all of our power systems typically are ground reference. So if you're grounded and you contact a circuit that is energized, you've completed that path and current will flow through you to that available ground path. And this is going to result in a particular hazard. The severity of that shock hazard is really going to be dependent upon several factors and stuff, which we'll talk about here in a few minutes. You could contact 2 points of a circuit that are energized at different potentials. This could result in a shock hazard. Current flowing through your body because, again, you've contacted 2 points of the circuit that are at different potentials. This will result in a current flow. You may contact something that has become energized, and you, in fact, are at ground potential. It may be because somebody's defeated one of the primary safety features of your product itself, which could be the ground conductor. If you have a product that is designed to be connected to Earth's ground, and you plug it into an outlet that is not grounded because somebody's either broke off the ground terminal or they've used an adapter where they're plugging it into a receptacle that doesn't have a ground connection, or they're using an extension cord where there's no ground, that could just have normal leakage current that is flowing through the enclosure that could result in a shock hazard. Or if the product is faulted, where there is a short between the enclosure of that product and the line, that product actually could continue to operate. And if that ground circuit is open, as soon as you come in contact with it, you've completed the ground path, and that shock could be lethal. There could be enough current flow through your body that could result in your heart going into fibrillation, or just your heart stopping, if at the least maybe a severe burn. So there's quite a few different problems and stuff it could result in defeating a primary safety feature of the product itself, such as the ground circuit. So one of the things that we're trying to get across here today is that you do understand the risk of electrical shock and injury. And essentially the severity of a shock that a person could receive is really influenced by several factors. The first one being the physical condition and response of the individual itself, the worse condition the person is in, the more susceptible they're going to be to possibly their heart stopping as a result of an electrical shock. They may not be able to get away from the voltage source or the current source that is providing that electrical shock. The path the current takes through the body, the worst path, basically arm to arm, hand to hand type thing, because it goes through your chest, right through your heart. Arm to leg, this could be a severe path. The duration or length of time that you're exposed to the electrical energy can have a huge influence on how much damage is going to occur. Okay. The magnitude of the voltage and the current. Okay. Why do I say the voltage? Well, you need a certain amount of voltage to be able to supply the current because your body has a certain amount of resistance also. So, the potential has got to be there to, create the current flow itself. So, this is why voltage is included in this statement here, and the frequency of the supply voltage. Higher frequencies can, result in some burns in some cases. The worst frequency it appears for electrical shock typically is a frequency that most of our stuff operates at, 50, 60 hertz. And the big reason for that, it can cause your heart to go into fibrillation much easier. Okay. We talk a little bit about, how your body reacts to electrical current. Basically, your muscles relax due to electrical impulses that are received from your brain. So, your whole body operates on some kind of electrical impulses and stuff here, through the nervous system of your body. We found through a bunch of testing that has been done over the years that essentially anywhere from about 0.5 to 1 milliamp of current is your perception level. 5 milliamps of current can create a startle reaction where you kind of jerk back, a slight shock is felt. You start getting around 6 to 25 milliamps in women, it can create a painful shock and the inability to let go. In men, the threshold is usually a little higher, somewhere between 9 to 30 milliamps, where it can produce this inability to let go. 30 to 150 milliamps can cause your heart to go into fibrillation, resulting in possible death. It can cause respiratory arrest. It is extremely painful. Currents, 10 amps, basically, pretty much, just immediate, cardiac arrest, severe burns, and these values are really based upon voltage levels of around 600 volts or so, or less. Where does some of this information come from? I know ANSI, American National Standards Institute, and Underwriters Laboratory, back in, I believe it was the 60s, conducted some experiments on a group of 20 men and 20 women that had volunteered to subject themselves to some electrical shocks. And UL had published a pamphlet, the effects of leakage current on the human body, I believe was the pamphlet itself. And in the back of that, there was a description of all these tests that were, conducted on these individuals that had volunteered to submit themselves to electrical shocks. And I think this was part of where some of this information basically has been derived from, with some of these tests You'll also find it on OSHA's website, and I think some of the NFPA 70E standards has some of this information in there also. So, it's available from quite a few different sources. Some of the numbers will vary slightly, but it's interesting how they come up with some of these values and stuff. Some of the people that have submitted to, volunteering to, get shocked. I take my hat off from them. I've been shocked too many times myself, over the years, been doing this for 44 years, and it's not a pleasant experience. And it's usually because somebody takes a shortcut or you make a stupid mistake, and, when you're working around voltage, you do your best to try to limit the hazard and keep away from it, but occasionally, things happen. You're troubleshooting a product that has a fault condition, and it doesn't always act the way it's supposed to. And you go in there and you start probing around, and sometimes you can make a mistake and end up getting shocked, even though you think you have everything shorted out. If there's an open circuit in there, you may not have a complete discharge path. But just a word to the wise if you're going through and troubleshooting circuits and stuff there. Okay. Performing product safety tests. What are some of the common types of safety tests? The first one is the dielectric voltage withstand test, or Hipot. Hipot, where did that term come from? It's actually an acronym for high potential testing. Okay. It is when you talk about a Hipot test, a lot of times people say, well, it's a breakdown test. That's kind of a loose term. If you're doing a breakdown test, typically a breakdown test is a destructive test. It's one where you increase the voltage to the point where the insulation fails. If you're doing that type of testing on your product, I wouldn't want to be the person that buys that product, because you're buying something that has been damaged due to the thing being overstressed, and it was done intentionally. So unless you're buying scrap, I wouldn't want to be purchasing that type of product and stuff there. But the dielectric withstand test is not meant to be a destructive test. This is a test that is done to verify the integrity of the insulation, to make sure that there are no faults within the insulation itself. And we'll talk about that as we go through this. Ground continuity test. This test is done to verify that there is continuity present within the grounding conductor of the product itself. It's not necessarily a point-to-point continuity test within the circuitry of a product. A ground continuity test is basically a test that is done strictly on the grounding circuit within the product itself. Ground bond test is a more severe continuity test. A ground continuity test basically is done typically at low voltage, low current, and it is just assuring that continuity is present. Where a ground bond test is really designed to detect the integrity of that ground circuit, to make sure that ground circuit could withstand a potential fault current that could be applied upon it. Okay. If you look at the specifications for a ground bond test, and you actually relate that to the fuse rating or circuit breaker rating of the product, you'll find that they're very, very close. Time delay fuse or circuit breakers are typically designed to carry a 200% overload for 2 minutes. Where you look at the specifications for a ground bond test, and a ground bond test is typically specified to be conducted for a 2-minute period, and it's done at twice the fuse rating of the product or at a particular current level, which typically may be the higher of the two, and it varies depending upon the standard itself. But we'll talk a little bit about that also as we go into the in particular test itself. Number 4, line leakage or touch current test. This is a test that is done on the product to measure the potential shock hazard that product could have to an operator or an individual that is touching the product under certain normal and fault conditions. Okay. So this is to measure a potential shock hazard that could exist within the product if you introduce some fault conditions into the product or possibly some potential errors in the input where the input potential may be reversed as far as the polarity, where your line and neutral conductors might be reversed, or you have an open neutral or open ground condition. What kind of potential hazards could exist to the individual if these fault conditions were introduced into the product itself? Okay. And lastly, an insulation resistance test. This is a test to verify the integrity of the insulation within the product itself. And this is similar to a dielectric withstand test, but it's typically done at a lower potential. It's commonly done as a maintenance test in many types of products. One of the big differences, it gives you a value back in the actual insulation resistance of the product rather than how much leakage current is flowing through the product based upon the applied potential. So, we'll talk about each of these types of tests and stuff as we go through this. Okay, the dielectric voltage withstand test. This test is a deliberate application of a high voltage potential between the mains input, which is essentially the primary circuit of the product, okay, and any exposed dead metal. Okay. If you're testing a class 2 product, it could be to the enclosure of the product, or again, any exposed dead metal. You may also be testing between isolated circuits, maybe from a primary circuit to a secondary circuit. So, the dielectric withstand test could be conducted, on any of these circuits. It's assumed that if the insulation can withstand this higher voltage potential or over voltage potential for a given period of time without breaking down, the insulation should be able to withstand and protect the user of the product from any electrical shock hazards, throughout the life cycle of the product itself. Okay. The test is designed to test and find possible defects in the design, such as inadequate creepage and clearance distances, as well as defects in the production process, such as pinched wires, damaged insulation, potential spacing problems and stuff also. So the Hipot test, or the dielectric voltage withstand test, is meant to be a non-destructive test, and it is conducted as both a type test and as a routine production line test. What is it doing? It's actually looking to make sure that the insulation does not break down. How do we define a breakdown? A breakdown is defined as an abrupt increase in the flow of electrical current or a complete failure of the dielectric material. Okay, so we're really talking about a catastrophic failure. The insulation fails, we have an avalanche of current flow flowing through the insulation, to the return of the product itself. It's a complete failure. The insulation will no longer support the potential that is actually being applied across it. Okay, it's a disruptive discharge. It's a discharge that bridges the insulation and, again, reduces the voltage across that insulation essentially to a zero value. So that's what a breakdown is. Okay. The Hipot type test, when we're doing a type test on a product, you're going to see some variations depending upon the safety standard, but the common type test potential between the main circuit and the chassis of the instrument is normally done for a 60-second period. Many safety standards may specify a potential of 2 times the voltage rating of the product plus 1,000 volts, which is equal to the RMS, potential of the device. Again, the potential is applied between the main circuits to earth, and if you're testing the insulation between circuits that may have direct contact with the individual, such as secondary circuits, if we're talking a medical device, the insulation between these circuits may be tested at a much higher potential. We might be talking 3,000–4,000 volt potential in some cases. So, this test is conducted under various types of fault conditions. Sometimes you, as a type test, will introduce humidity conditioning to simulate a very wet environment. It may be after a rain test that has been done on the product. So there are a lot of more severe testing in a type test is done versus a routine production line test. So if we're talking a Hipot test during a type test, they're typically done at for a longer period to determine the adequacy of the insulation, again, looking to make sure that creepage and clearance distances are proper based upon the design of the product itself. Okay. The routine tests that are performed in a production environment, these tests are normally done at a much shorter time period. Why? Well, we're trying to get a product out the door. So, production time is, one of our most valuable things going on out in the production environment. How can we get the product out the door in the least amount of time possible? So, one of the things they do is they reduce the time that this test actually takes. Normal routine production line Hipot test is normally conducted somewhere between a 1 to a 5 second period. With connecting up products and stuff, if we're talking high-speed production lines and stuff, sometimes between products you may be talking, 10, 20 seconds, from one product to another. So these things are moving down the line very, very quickly. So, you want to test these things as quickly as possible. But yet you want to make sure that the insulation is still being tested properly. Normally in a routine production line test, the test potential that is applied during the type test is normally increased by a factor of about 20%, and that time period is normally reduced to a 1 to a 5 second duration. Again, keep in mind that the Hipot test in the production environment is designed to try to find faults in workmanship errors. Again, damaged insulation, something that could happen, during the production, process itself. Products, Class 1 products are tested at a different potential than a Class 2 product. What is a Class 2 product? Class 2 product is a double insulated product, where instead of having just the basic insulation of the product as the first level of protection to guard against electrical shock and the grounded metal enclosure, you have 2 levels of insulation. You have a reinforced insulation that basically may be the basic insulation and some type of supplementary insulation between what are normally current carrying conductors and what not meant to be a current carrying conductor. And when that occurs, normally the test potential that is applied to test a double insulated product is twice the voltage of the potential that is applied for a Class 1 product. So a Class 1 product might be tested at 1500 volts, where a Class 2 product is now tested at a 3000 volt potential. This is very common depending upon the safety standard that we're talking about. Okay, let's look at some of the standards. IEC 1010 2010, which is the standard for laboratory equipment. Both as a type test and a routine production line test, this standard says no flashover of clearances or breakdown of solid insulation material shall occur during the test, nor shall the device indicate a failure. So whenever we're testing the insulation within the product, no flashover is allowed, no breakdown of solid insulation is to occur during the test. So, that is, the failure condition that we're looking for, looking to make sure that does not happen. Okay. IEC 60335, which is the safety standard for household appliances. As a type test, it says no breakdown shall occur during the test. The high voltage source, here they're specifying the Hipot itself, should have the capability of supplying at least 200 milliamps short circuit current. The trip current shall not be less than 100 milliamps, and this is for test voltages of 4,000 volts or less. So, here the trip current of the Hipot tester as a type test should be set for 100 milliamp trip, and any current below that basically is allowed to to pass. As a routine production line test, though, things are a lot more stringent from the standpoint that the trip levels normally are down to about a 5 to a 30 milliamp level, depending upon the product itself. No breakdown shall occur. It's assumed that when the current exceeds 5 milliamps, that is considered to be a breakdown. However, this level can be increased up to 30 milliamps for appliances that have higher leakage currents. The high voltage transformer must be capable of maintaining the specified test voltage throughout the duration of the test at the limited current. So it's got to have the capacity to maintain the output potential, all the way up to the the trip current. So we're basically talking about a tester that has a regulated supply that's good enough to make sure that the test potential is not going to sag during the test itself. Why is that important? Many a times, if you look at some of the old analog Hipot testers and stuff that were out in the market, one thing you have to consider is if you're only doing a 1-second test, typical response time of the metering network is anywhere from 2 to 3 seconds. So the meter will never stabilize in on a reading before the test is over with. So how do you know that you're actually applying the correct potential? One way of doing that is to make sure that you do have a tester that is regulated as far as the output voltage potential, or have something that is a brute force tester that has a large current capacity. One of the safety precautions, I'm going to back up one slide here, is that if you're using a tester with 100 milliamp output on your production line, you have to be very careful with the training and skill levels of your operators. Most of the time, the people in the production environment do not have the training of the individuals that are doing the testing from an engineering environment. You know, they're not degreed electrical engineers or technicians, so they may not know all the hazards that, you know, and how to avoid them, even though the safe OSHA standards dictate that they should. But 100 milliamps of current can be lethal. If the operator makes a mistake with that, it may be the last one they will ever make. Keep that in mind. You know, when you set up your workstations, make sure that the workstations are guarded so you are protecting your operator from any potential electrical shock hazard. Doing Hipot testing or safety testing should not be hazardous to the operator. Keep that in mind. I can't stress that enough. Okay. Hipot failure, EN 50116 for information technology. Routine electrical safety test in production. This is the standard that actually describes that. One thing I like about this standard, it is gives you a little bit more of an indication of why you set your trip point, you know, to a value, or where should you actually set it at. It says no insulation or breakdown shall occur during the test. For the purpose of this standard, an insulation breakdown is indicated by the trip current, which is defined as any significant increase from the steady state current measured during the electrical strength test. And the duration of the test typically is 1 to 4 seconds. Okay. All right, so what are they saying? Well, if I do a Hipot test on my product and it draws 1 milliamp of current, I should be setting my trip current something that is a little higher than that. Allow for some deviations in, you know, a little bit in the product itself, but I shouldn't go absolutely insane on setting something that, you know, is, let's say, 100 milliamp trip setting. Why would I want to set it for 100 milliamps? Well, the standard may allow me to, but you know, you could have some issues that might come up where you could have a high resistance fault within your product that you may never detect if your current trip threshold is set that high. I've seen it. I've had customers have products where they've had some problems, and well, the standard will allow me to set a trip current that was much higher, so I went to the maximum, but yet if they would have set it to something that was a little higher than what the product normally would draw, they would have caught the defect immediately rather than 6 months down the line. Now, you know, you have a recall potential that you may have to worry about on, hey, do I have to recall that product? Is it a potential hazard, you know, to the operator itself? You know, is my equipment working properly? This kind of stuff. Okay. Test equipment shall be provided with a means to indicate the test voltage. and the insulation breakdown. Should have either an audible or visual indicator, some type of alarm, to indicate that a failure has occurred. Okay. The trip level is determined by the manufacturer. Okay. Where do you set your trip point? Okay. This is manufacturer of the test equipment. Manufacturer of the equipment under test is how that should read. Okay. You make the determination, where do you set your trip point? Okay. The factory, if you buy a Hipot from us, it's probably going to have a default trip setting of either 5 or 10 milliamps, depending upon the product that you end up purchasing. Did you change it? I've seen testers that, well, that's what the factory set it for when, we shipped it, we've never touched it. Okay. It's something that you may want to change. If it works for you, then you might want to go for it. We try to set it for a value that is close to most of the agency standards. Okay. Trip current level should be set to a minimum practical value as reference. This value is usually in the order of a few microamps if you're doing a DC test or a DC measurement. If you're doing AC testing, the current that flows through your filter capacitors should be taken into account. Where do you set the trip setting at? Okay. Second line of defense for providing protection for electrical shock is essentially, if you're talking a Class 1 product, it's a grounded metal enclosure. If you're talking a Class 2 product, it is the second level of insulation within the product itself. Okay. If you have a Class 1 product that has a grounded enclosure, you must test for continuity between the ground blade of the attachment plug and that enclosure. Okay. That is a normal requirement as a routine production line test for your products. Okay. If it's a Class 2 product, then basically your test potential is normally 2 times the AC potential that is done for basic insulation alone, within the product itself. So, if you're doing a 1500 volt test for basic insulation, then the double insulation would be tested for the most part, usually around a 3000 volt level. Okay. What is a good indication of a good ground? Well, according to the National Electrical Code, which is what defines a lot of our standards or information here in the U.S., National Electrical Code basically states that an effective ground path must be permanent and continuous. It should have the capacity to conduct any fault current that is likely to be imposed upon it, and it should have sufficiently low impedance, which will eliminate any voltage to ground or limit the voltage to ground, and to facilitate the operation of any circuit protection device. What the hell does that mean? Basically, it says that the ground circuit really shouldn't act like a fuse. It should be able to handle any fault current that is likely to be imposed upon it itself, and it's got to keep the voltage low enough so if I'm holding on to that product when a fault occurs, I shouldn't receive a shock due to the voltage that's being induced onto the enclosure of that product, and the capacity of that circuit conductor should be large enough that will allow my fuse or circuit breaker to trip off and shut off the potential going to the product to eliminate any fire hazard or any other potential shock hazard that should occur. So that's what that ground circuit is designed to do. Okay. Many of the UL standards, when it talks about doing a continuity check, says you can use any kind of a battery buzzer or the like to indicate the presence of ground. Some of the standards are now starting to be revised where they are saying that the maximum resistance of that ground conductor should be 0.1 ohms or less. Which kind of complies with the the ground bond specification and stuff also. So, they're starting to be revised and stuff as some of these standards are being rewritten. The battery buzzer combination is a little dangerous. You can have one conductor of your line cord and pass a continuity test, but there's no way in hell it's going to be able to handle any fault current. And how important is this ground circuit? Well, if you look at this diagram that we have here on this slide, this shows a circuit breaker panel over here, and we've got our circuit breaker. This is our transformer feeding power into our building over here, and this might be the line cord of our product or the power conductor coming into the product itself. If the insulation fails and that shorts out to the enclosure of the product, now if my ground circuit is intact, what would happen? Well, this ground circuit should have a low enough impedance that will allow for this current to flow back to the source, back to ground, and essentially cause my fuse or circuit breaker to open up. Okay. That's what should happen. Okay. But what happens if this ground circuit is not there? Okay. If that ground circuit is not there, my current still flows into my product, and now my whole chassis will become energized. And this is going to be at whatever potential is coming out of this transformer feeding power into this. With this ground circuit not being present, a fault could occur here as long as that insulation is not shorted to the neutral side of the line. This tool or product could continue to operate. So now anybody that, let's do a little stick man out here, okay, if I'm standing here in contact with this and in contact with earth, that current is now going to flow through my body back to ground, and I'm going to be dead, okay, because this insulation was, or this ground circuit was defeated. Somebody cut off the ground pin of this tool, okay. So, the importance of this ground circuit is huge. If it is not present, it can create a hazard that could result in death to the person that comes in contact with it. You see articles every day that, where people have gotten electrocuted because, products were used near a swimming pool or whatever, and the ground circuit, they plugged it into a two-prong outlet. They weren't using a GFI protected outlet. So, all sorts of different things end up resulting in the person being shocked or electrocuted. Okay. Anyway, continuity is a routine test that is done on each and every product. We test, according to the standards, the ground circuit between the blade of the attachment plug to any exposed dead metal. Some standards say any indicating device can be used, battery buzzer combination of the like. The problem with that is most of these little pin light batteries and some of this stuff, it can pass at 8 ohms or so. That is not a good ground. you know, if you take a 120 volt circuit, you divide it by, let's say, if it has a 15 amp fuse, okay, if that circuit, in order to, you know, that fuse can carry 30 amps of current for 2 minutes without blowing. So if I take 30 divided into 120, that comes out to 4. If my resistance of my ground circuit is higher than 4 ohms, it will never allow enough current to flow in the circuit that will allow my fuse or circuit breaker to pop. The standards now that specify a 0.1 ohm continuity, I applaud. They are finally, you know, specifying something that makes sense for doing a continuity test. This standard of you know, any indicating device is long overdue to be obsoleted. Okay. Ground bond test. How does it differ from a continuity test? It tests the integrity of this ground circuit by applying a high current to make sure that this ground circuit within the product can withstand any fault current that could occur. And it is normally tested at 2 times the maximum fuse rating of the product or 2 times the fuse rating of the receptacle that that product could be plugged into. This is coming up in many, you know, standards. So if I can plug my product into a 40 amp receptacle or a 20 amp receptacle, that could carry potentially 40 amps of current for 2 minutes. I got to do a 40 amp ground bond test on my product unless my product is fused. And the ground bond test essentially applies a high current through this circuit and measures the potential voltage drop across this circuit. And based upon that, it calculates the resistance. And if it exceeds 0.1 or 0.2 ohms, it will fail. Why is there a difference? Well, it depends upon whether I have a permanently attached line cord or one that's removable. If I have a line cord that's removable, my maximum resistance typically of my ground circuit cannot exceed 0.1 ohms. If it's above 0.1 ohms, or if it's a permanently attached cord, then I can go up to 0.2 ohms. Again, here's some standards that kind of talk about the test itself, repeating some of the same things that I just stated. If you're testing a 20 amp branch circuit, that branch circuit could potentially, you know, would not interrupt until 40 amps of current was exceeded. You know, so this test basically is 2 times the fuse rating, or 2 times 20 amps, so this would be a 40 amp ground bond test. Again, this is based upon 60950 standard for information technology. The routine production line test of the European norm standard EN 50116 is either talks about 1.5 times the capacity of the ground circuit, but not more than 25 amps AC or DC for a period of 1 to 4 seconds. So as a routine production line test, the duration of this test is much, much smaller. Okay. Line voltage leakage test. I am running a little behind, people. I apologize, but this is essentially a touch current test. This test is conducted on a product that is designed normally to measure the current that could flow through a person while that product is actually operating. Okay. They utilize measuring devices which are capacitive and resistive networks that simulate the impedance of the human body, and they operate the product under what is considered normal and single fault conditions at 110% of the rated input voltage and measure how much current could flow through that individual. here's a circuit for doing a simple earth leakage test or an enclosure leakage test on a product. This is for a product that has a hot and a neutral conductor. Let's say where this product is rated for 120 volts. So you have a line, a hot conductor, you have a neutral conductor, and in this particular case, we're talking about a a product that may have a ground conductor also. Okay. S1 is on the neutral side of the line. S2 is a double pole, double throw relay that is designed to either put normal or reverse polarity into this receptacle to operate the product. And S3 will either open or close the ground circuit. The MD circuit over here stands for measuring device, and this simulates the impedance of the human body. My current meter is essentially here across this measuring circuit. It utilizes this impedance network as its input and measures the voltage drop across that network, which in turn calculates how much current flowing through this circuit. Okay. So the product is connected into, to this enclosure. It's turned on, and you have to conduct a series of tests, basically in all possible combinations of all these switches, while measuring how much current could either flow through the ground conductor itself. If you're measuring the earth leakage current, then this measuring circuit would be in series with the ground conductor, or from the enclosure of the product back to the neutral side of the line. So the device would be plugged in, turned on, and you would typically want to do all your open neutral circuits first, because this would give you the highest leakage current. Why does that occur? Okay. I would first off apply 132 volts in on my input going into this circuit. Line power comes in through here, depending upon the positioning of this relay. If it's in the position that's shown here, I got line power coming in, going in through this conductor, feeding into my product itself. This is all setting at 120 volts in reference to ground. In this particular case, my neutral side of the line should also be ground reference. This is my reference point. Okay. So my device should be setting on a non-conductive surface where it is not in contact with earth. Otherwise, my measuring device would be essentially shorted out. So now I got 120 volts feeding into my product, going through all the circuitry in the product itself. This is setting at 120 volt potential, feeding back in to the other side, which comes up to my switch, which is open. So now I have no return path. So all this circuit is at 120 volt potential in relationship to this earth ground. This creates the highest leakage current in my device, just due to capacitive coupling of all the circuits. My circuit from my hot side. Let's change this a little bit. We'll make it a little smaller lines. Let's change the color. Okay. So what I have between all these circuits, there is a certain amount of capacitance. And what is a capacitor? It's two conductors separated by an insulator. So we're testing this insulation. We're measuring the leakage current on that side. We're measuring the leakage current on this side of the line, which is setting at a 120 volt potential. So all this is in parallel, and all that current is flowing back through, you know, my measuring device, trying to get back to my reference neutral side of the line, which is ground reference and stuff here. This would be worst case condition. Okay, reversing this relay S2, changing the polarity of this, really wouldn't change this. My leakage current would be approximately the same because I still have no return path past this neutral switch over here. So open neutral condition basically gives me worst case condition on leakage current flowing through my product. Changing the polarity of my input in this particular case would not make any difference as long as my neutral side of the line is open. What happens when this switch is closed? Okay, let me back up here. When I had this other circuit, all these measurements were done with my ground circuit open. Okay, if my ground circuit were closed, essentially all my leakage currents basically would drop to zero because my measuring device essentially is shorted out. I have ground on this side of the line. I have ground also through my ground conductor going to the enclosure, so I've got ground on both sides of the line, so I would see no leakage current when this ground circuit is closed. When the product is operating, I see different leakage potentials depending upon the input polarity based upon the design of the circuitry within the product itself. So, you know, this test is designed to test how much leakage current is actually flowing through the product under different, you know, conditions and stuff here. Some of the impedance networks, 60601 specifies essentially a value for R1 of 10K. The R2 is a 1K ohm, and this capacitor is a 0.015 microfarad capacitor. My voltmeter is strapped across this. So this is essentially my current meter that is essentially my measuring device that appears in all of our diagrams and stuff to indicate, you know, how we're actually making that, you know, the current measurement itself. Okay. There are multiple types of touch current test. Depending upon the type of product, you may be doing an earth leakage current, an enclosure leakage current, a patient leakage current, an applied part, mains to an applied part test. So there's multiple different types of tests that kind of all fall in this touch current type leakage current category, and they get involved into quite a few different switching configurations. Unfortunately, that's a whole webinar all in itself that I don't have time to get into today. But lastly, the insulation resistance test. This test is done to verify the integrity of the insulating material. No insulation is perfect, having an infinite resistance. It may be beyond the capacity of the measuring instruments that you're used to make the measurement with. Electrical current that actually flows through or across the insulation is a leakage current, and based upon that leakage current and applied voltage, we determine essentially what the insulation resistance is of the product itself. Insulation resistance tests are normally conducted at 500 to 1,000 volt potential on most products that we as consumers use on a daily basis. Insulation, don't get me wrong, insulation resistance test, you know, can be as high as maybe 10,000 volts, depending upon the type of product and stuff that you're testing. Typical high voltage applications, this kind of stuff, may require a much higher insulation resistance test. But this test is probably the least commonly specified test because it is testing the same insulation that is being tested during the dielectric withstand test or the Hipot test. It is considered to be a little bit less stressful than a Hipot test because it's typically done at a lower potential. So you're not putting as high a stress on it as what you would be when you're doing a withstand test on it. It's also done normally always using DC, again 500 to 1,000 volt potential, where most withstand tests it could normally is specified as an AC test potential. If you do a DC test, it's usually done at the peak value of whatever the RMS test potential actually is. The time required to perform an insulation resistance test is going to vary depending upon the product that you're testing. Products that have a much larger capacitance require a longer duration IR test, and you must allow for enough time to charge up the device under test before you take an insulation resistance reading. If you take a reading while that capacitance is still charging, it's going to be an erroneous reading because you're measuring essentially leakage current or charging current rather than the actual leakage current due to the actual insulation resistance of the product itself. So when you apply a potential across an insulating material and you charge up that capacitance, you see a inrush of current that is quite high at first because that capacitor essentially looks like a short circuit, and once you stop increasing your voltage, you will see the leakage current then start to decay as that capacitance actually charges up over time. Eventually it'll get to a steady state leakage current, and that's where you want to take your measurement sometime once this current level basically has stabilized in order to get a true insulation resistance reading of the device that you're going through and testing. If you're attempting to compare insulation resistance measurements on a family of products, there are several parameters you must take into account. You must make sure that you're using a consistent delay time in taking your reading. Again, this is important because of this charging curve that we talked about. I recommend making sure that you're using the same type of test equipment. Many insulation resistance testers have got different capacity power sources. They have current limiting resistors that can vary how much charging current is available to charge up the capacitance of the product, which affects this delay time, which affects how fast the thing charges up. So if you're trying to compare insulation resistance readings, I recommend write down the model number of the equipment that you're using, so you're essentially comparing apples to apples. If you can use the same type of instrument each time, it is very helpful. Otherwise you may want to make sure you wait long enough until the charging current stabilizes before you take a reading, to make sure that you are looking at a consistent reading. Temperature has a great deal to do with your insulation resistance measurement also. If you're testing motors and stuff like that, there is a temperature conversion factor that must be taken into account. There's actually an IEEE standard for doing insulation resistance testing. Offhand, I don't remember what it is. It's been a long time since I've looked at it, but I think it's, I'm not even going to, guess. I don't recall what the number was offhand. But typically, high insulation resistance values indicate good insulation, while relative low insulation values point to relatively poor insulation. These values can vary based upon temperature and humidity. What are some of the minimum limits? Here's a couple product safety standards that gives you a couple examples. And these values, I think, are extremely low. EN 60204 for safety of machinery specifies a 500-volt DC insulation resistance test between power conductors and protective bonding circuits. Minimum insulation resistance value should not be less than 1 megohm. 60335 for household appliances specifies a 500-volt DC test with a 2 megohm minimum insulation resistance test. Senelec basically requires this test as a 100% production line test. So, okay, that concludes all the material and stuff. Again, I apologize. I went over about 17 minutes over the projected 1-hour time limit. Our next webinar is April 10th. It is on ground continuity versus ground bond testing. It is also at 10 a.m. If you would like a copy of this presentation, you can contact Jim Kennedy at the email listed here, jimk@asresearch.com. Our phone number and contact information is also listed here. If you have any questions and stuff that were not answered during this presentation, we will get back to you, make sure that they do get answered, this kind of stuff. Unfortunately, like I say, I ran over quite a bit on this. We'll leave it open just for a couple minutes just to see if there's any other questions and stuff that do come in that have not been answered. Otherwise, I thank you all for attending, and please join us on April 10th for our next webinar. Again, this webinar has been recorded, and it will be available tomorrow on our website. If you go www.asresearch.com under events-training and then webinar archives, you can pull up this webinar. Use it for doing training and stuff. Anybody that has not seen it that you would like to recommend, they can hear basically the same presentation that I just got or just gave you. So with that, again, thank you, and we're going to go ahead and close this out. I didn't see any more questions and stuff come in, so thanks for attending.